Recording on.
Okay, hey everyone, welcome. So in this session, we are going to discuss a couple of problems. Trying to share the screen. Just a minute. Okay. So in this problem, last week we discussed about the balancing of binary tree, right? Like given a tree, whether it is balanced or not. That is one thing. And the next one we are going to discuss is minimal tree. So we will repeat we'll review this problem again and then we'll talk about minimal tree. So how to construct a minimal binary tree, what is minimal binary tree and how to construct, and then we will talk about heaps if we have some time. So let's iterate the last week problem. So here is the thing what we have, right? So let's construct, this is very simple tree. So let's construct this one here. Okay. Okay, let me put this one on the other side. Okay, so we have the tree like this, right? Here is A, and A left is B, and A right is C. Okay, and B left is D, and B right is E. This is what we have, right?
Yeah,
Now tell me, is this balanced or not? By just looking at it, did you guys remember the definition of
yeah, it's
balance?
balanced.
It is balanced, right? Because if you look at here, the heights, this side is on the left side is the height is 3, 1, 2, 3. The max height is 3, on the right side 2, which is equal to 1. So the difference is 1. So it's still balanced. So so in this situation, what will happen if you run our algorithm, right? So our algorithm is this one. So the first condition is balanced. Okay, so what will happen is we are calculating the height of the root. Height of the root is basically, in order to get the height of the root, we will do the recursive way here, right? So if the height is -1, if in case at any point of time, if we get -1, then we are saying it is not balanced. Okay, so let's say, let's look at here. What we did is, after we calculating this first step, is balanced or not. Now failure case, we are adding one more node F. We are creating one more node F, add extra node to E. So we are adding F to the right of E. That means we are adding F here. Okay, so maybe let me put in a different uh, okay, now if you calculate the height, so E is tree balanced is basically we are calculating the height of the root, right? If you calculate the height of this whole tree, what is the height of the whole tree? If you start from here A, what is the maximum height? Maximum
Four,
height of the tree,
four.
4, right? Yes, 4. But in technically, if you call this method, it has to return 4. But what we did is we modified the logic. We modified the logic in such a way that if this tree is not balanced, if the tree is not balanced at any point of time, it will return -1. If the tree is balanced, it will return the normal height. That is how we modified the algorithm. Basically, this algorithm is not it will not return the height of the root or height of the tree all the times. Even though it says get like height of the node or height of the root, even though then it says like that, we modified the algorithm in such a way that it will return -1 if the tree is not balanced. Okay, if the tree balanced, we'll get the height. Now let's see how it works, right? So now let's go with the base case. Okay, let's go with the positive scenario. So now we got the root. Okay, root is A, right? Root value is A. So what are we doing here? If the root is null, return 0, which is pretty base scenario, right? If there is no elements, what is the height? 0, right? If not, what are we doing here is left subtree height. and right subtree height. So what is the way to calculate? This is the one I told you in the beginning. So if you have the tree, let's say this is the tree. Okay, some element A here, and there are some nodes here, there are some nodes here. Okay, now I want to calculate the height of A. I want to calculate the height starting from this node, this whole subtree. What is the height? How to calculate the height? We need to
Left
get the height.
subtree and the right subtree, height of the left subtree and the height
Exactly.
subtree.
Exactly. So that is how to do it. Get the left subtree height, left subtree LST, let's say left subtree height, and this is right subtree height. Okay. Calculate the left subtree height, calculate the right subtree height, and then what we need to do?
Add 1.
Exactly, because if you are doing this is like three levels. This is like you know this is like five levels. You are adding one more level, right? This is like levels means basically the height. So let's say this one is three levels. The height of the left subtree is three, and the height of the right subtree is five. So what we need to do before adding one, this is another level you're adding. A is another at another level, right? Because this is a parent for this whole subtrees. So are we going to, so we need to take maximum of these two, correct? So the right subtree is already bigger. So we need to take the maximum. What is the maximum here? 5 plus 1. That becomes 6. So we need to understand, like you guys need to understand this concept. Is it clear or not?
Yeah, it is clear, Suresh.
Right? So if you want the height of the subtree, which includes A, this is the subtree. Let's assume that this is not the full tree. This is also a subtree. If you want the height of this subtree, where if you include A, what we need to do is we need to calculate the height of the left subtree. We need to calculate the height of the right subtree and take the maximum out of these two and add 1. That is the whole logic of uh, finding the height. Okay, but at any point of time, what are we doing here is we are calculating those two. See this, we are calculating. Check the height of the left subtree and check the height of the right subtree. See this, immediately we are not even doing calculations, we are not even doing these maximums or minimums. We are not doing that. We are simply having one more condition. At any point of time, if you get -1, return -1. That means if you get, instead of 3, let's say instead of 3 you got -1 here, not 3 you got -1, or instead of 5 you got -1. So either of those, if the left subtree height is -1 or right subtree height is -1, what are we doing here? We are immediately saying the height of this whole subtree is also -1. This is the modified logic we did. See, so that is the condition here. When we do the -1, we will tell you. So -1, how the -1 will come here is, this is the logic. Check the difference in heights of the left subtree and right subtree. So in order to calculate the height, we don't need to do the difference or anything. So what we did, we just took the maximum, we just added 1. We no need to do the difference of 5 minus 3 is not required in a normal algorithm where you want to find the height. You don't need to do this difference, but we are doing, because we want to calculate the height only if the only if the subtree is a balanced subtree. Okay, that is the reason before we calculating the height, before we doing this, we are calculating, is this difference greater than 1? That's what we are doing here. Absolute means it doesn't matter whether you do the left minus right or right minus left. Okay, we'll take the absolute value. Okay, so if the difference is greater than 1, okay, that means even though if let's say instead of 3, you got the left subtree height is 5 and right subtree is 3. No, this is actually the correct value. So 3 minus 5. 3 minus 5, what happens? 3 minus 5 equal to minus 2, right? And what is the absolute value of minus 2?
2.
2. Absolute value is 2. Just absolute value means it will ignore the minus basically, right? So now the difference between left subtree and right subtree is 2. There is a 2-level difference. This has 3 levels, and the right subtree has 5 levels. So there we are breaking the condition of balancing, right? So that's why if the difference is greater than 1, immediately return the minus 1. Don't return 6. Don't return 6. In fact, the height, if you're starting at a, the height is 6, but instead of returning 6, we are returning minus 1. Okay, this is how they will return the minus 1. So otherwise, if it is not greater than 1, if it is less than 1 or 0, let's say if you get the height on the right side is also, let's say the height of the left subtree is 3 and the height of the right subtree is also 3, what happens? The difference, 3 minus 3 equal to 0, which is good. Or the right subtree is 4, not 5. Now the difference is 1, that is also fine. As long as these two are balanced, that is good. So either it is 0 or 1, we don't return minus 1, we will go to the actual step. Take the maximum, add 1 and return the height. Take the maximum of left subtree, right subtree and add 1 to it. Is it clear now?
Yes, Suresh. Yeah.
Yeah. So now you understand why we have the if conditions here. So at any point of time, if so basically when you do this, right? So basically, what are we doing here? We are recursively calling the left. So in order to calculate the height, so we want to calculate the height at this location. We want to calculate the height of a, but in order to calculate the height of a, we are calculating the height of left subtree using the same method, same recursive method. We are calling height of the node dot left, right? And similarly, we are calling the same method, recursive method, using right node dot right. So at any point of time, we got the minus 1. There is a chance, right? You are calling same method. You are calling same method. So this is minus 1 means this returns minus 1. That means what is that means? So there is some nodes here which is not balanced. There is some subtree of this tree is not balanced. You no need to compare with this one, right? If this is not balanced, you no need to compare this. You no need to calculate the height of right subtree. What is the point of doing it? You already know the left subtree is imbalanced. So simply we are returning minus 1 here. Similarly, if right subtree is also same thing. No, this is fine. This returns 3, not minus 1. Now we are calculating right subtree height. If in case the right subtree height returns minus 1, then you no need to do anything because this is imbalanced. The right, some of the nodes here, make the subtree imbalance. So no need to calculate any of the things. We simply return minus 1. That is how we get minus 1 at any point of time. So then it will be the whole result will be minus 1. Got it?
Yeah.
So now we can execute and see. Now I told you the whole story here. Now if we execute, okay, let me draw again. A, B, C, D. So we got this one. We got A and B and C and D. Okay. Now what happens? This is balanced. So if we calculate this, so yeah, so we'll start with this. And first, initially, A is node. Node is A, right? So now left subtree height. In order to calculate the left subtree height, we will call the height of the node. So we will call the same method using B. right? So again, it will come here, and B is not equal to null. It come here, left subtree height, height of the node of left, height of the C. It will call again the same method using C. Now C is also not equal to null, and come here, left subtree height, height of the node dot left. What is the C dot left? Null.
Null.
Null, right? So now that will become here. Now node is null. Go here, node is null, return 0. Okay, finally we got 0 here for the left subtree height. Now we are at the C level again. Now right subtree height. Get the height of the right subtree. What is the right of C? Is also null. So we get 0, right? So we got left subtree height 0 and right subtree height 0, right? Now both are not -1, so we don't return -1. What we do is, we will do the difference of 0 minus 0 is 0. Difference is 0 minus 0 equal to 0, which is it greater than 1? No. Now max height, left subtree height is 0. Max of 0 and 0 is 0 plus 1. Finally, this returns 1 to B. Right? Now you are at the B again. So now you got the left subtree height as 1, and again you do the right subtree height. Right, height of the right subtree node dot right. It will do the same calculation, right? It will return the 1 again. Correct? Now, what is the difference between the left subtree height and right subtree height? 1 minus 1. 1 minus 1 is 0, which is good, which is not greater than 1. So now, maximum of 1 and 1 is 1 plus 1. Maximum of left subtree and right subtree, and we are adding 1 to it. So now, the height of this B is 2. The 2 will be returned to the top. It's 2, right? So this is one level, this is another level. Correct? You guys following so far?
Yes, yes, yes.
Now you are at the A again. So you got the left subtree height is 2. Now you are at A and you are calculating the right subtree height. Now you are calculating right subtree height. So right node dot right. So now you are at C. If you are at C, there is no left, there is no right, and similarly you get 1 here. So this will return 1. So now you are at A again. So you got left subtree height as 2. You got the right subtree height as 1. Okay. Now check the difference. 2 minus 1 equal to 1, which is not greater than 1. So what is the maximum of 2 and 1? Maximum is 2, and you are adding 1 to it here, line number 44. And that will be the height equal to 3. That will return 3. So that is the final answer written from A equal to 3. That's correct, right? This is first level, this is second level, and this is third level. You can count from top or bottom, doesn't matter. So height of the whole tree is 3. Let's check that. So you can put a breakpoint. We already have a breakpoint there. So we can. Okay, so now if I go and run with start debugging, so we will see. For this particular first algorithm, we will get height equal to 3. Okay, go ahead, continue. What is the height? 3.
Okay.
Got it? So it will go the same way. As I said, it will execute one by one. It will recursively execute, and finally we will get the height as 3. So now what happens here is we are adding one more node, F. Okay. Now what will happen? If you node F, okay, let's go back to the same structure here. If you node F to the tree here, what will happen here is, so okay, we'll do again. Simple. A, B, C, D, E, and you are adding F here. Okay. So now we calculate. Now it will start with the same thing, right? It will start with A. Initially, it starts with A, and we want the height of the left subtree and height of the right subtree. Now it will go to the left subtree height. That means it will call with node dot left, which is B. Node dot left is B, right? Now it will start with B. Now you are at B, B not equal to null. You want the left subtree height. Now it will go to the D, and at D, now you are at D, D not equal to null, and left subtree height is 0, right subtree is 0. Finally, it will return 1. So 1 will return to B as a left subtree height. Now you are at B again. Okay, you want the height of the right subtree. B dot right is E. Okay, calculate the height from E. So now you are at E, E not equal to null, and left subtree height is 0 because there is no nodes here, right? Left subtree height is 0. Now let's calculate the right subtree height. Right subtree height is, that means E dot right. Now we need to calculate the height of F. So now node equal to F not equal to null, right subtree height is 0, left subtree height is 0, right subtree height is 0, and finally the difference is 0, and the maximum and the height of the F is 1. That will be returned to here, right? Now you are at E again. So you got the left subtree height is 0, right subtree height is 1, and what is the difference is 1, and now you are calculating the max of left and right and adding 1. So maximum is 1, you're adding 1, so 2 will be returned to here. You guys following so far?
Yes.
So now you are at B
Yes.
again. You got the left subtree height is 1, right subtree height is 2. Now you calculate the difference. 1 minus 2 equal to minus 1, which is equal, like absolute is 1. So 1 is greater than 1. No, it's not greater than 1. Now what is the maximum of these two? So maximum of 1 and 2 is 2, and we are calculating 1, 3. The 3 will be written to A. Correct? Because 3, if you look at, if you start counting from B, see that this is one level, this is another level, and this is another level. 3, right? So this left subtree height is 3. Got it? Now you are at A again. So now A left subtree height is 3. Let's calculate the right subtree height. So right subtree height means C. C will return 1 because it's just one node, right? Now you are still at A. Let's calculate the difference. Left subtree height is 3 and right subtree height is 1, which is equal to 2. 2 is greater than 1. Yes. See, this will be satisfied. So instead of returning a 4, in fact, it should return the height as 4, right? So I'll get the maximum 3. 3 plus 1, 4. Instead of returning 4, you will get minus 1 because of this condition. You guys followed so far?
Yes.
Yeah.
That is here. So I can continue and show you. So we got 2 there. Okay, this is for the first iteration. Yep, see that we are adding F. If you add F there, and then we'll see what happens. See, we are returning minus 1. So left subtree height is 3, right subtree height is 1, and 3 minus 1 is difference is 2. 2 is greater than 1, so we are returning minus 1. If you return minus 1, it will return false. Okay. Oh, what happened? Okay, we are returning false. Yeah, I think it crashed. I think so, but you understand the whole point, right? So if I show you the output, oh, it just crashed, so I may need to run again. So without debugging. So it will return true and for the first one, and it will return the false for the second one. That's it. Is it clear now?
Yeah.
Yeah, it is tough. The understanding the recursive algorithm is always tough. So see, once you add the f, it returns the false. Yeah, I definitely recommend buying that the cracking the coding interview. They explained these concepts. Actually, they explained why are we doing this, and initially, even before putting the actual algorithm, they put different methods. They put some wrong methods, or they put some other methods which will take more time complexity wise. So that is a really good book where you can learn more about different approaches and how to think all those things. Because I'm just giving you the right algorithm, because I don't want to give you 3 4 methods and finally give you the right algorithm, because that will take again extra time. So if I want to discuss all the approaches, right? So even just explaining one approach itself is taking long time, right? That book talked about different types of approaches. Some of the problems, they explained 3 4 approaches, and they explain pros and cons of each approach, and finally they present the optimized one. you know that will be the good one. So some of the problems they explain really well. Okay, so if we are good, we can go to the next problem. Okay, and before going that, do you want us to calculate the complexity of this algorithm? What is the complexity of this algorithm? So usually, normally in a normal case, the complexity, if you are going this kind of level by level, right? So what is the complexity? You are not you see, if you look at here, once you calculate the left subtree height, if in case this return 3 instead of 3, if this returns -1, you don't calculate even the right subtree height, right? Let's say this right subtree has one element. Let's say this has million elements. You don't do that. If as soon as one side you got -1, you simply return -1. That's what we are doing here, right? If you look at here, so at any point of time, either left or right is -1. We are not calculating the other side of it. So you never. So in an ideal case, or in some cases, you don't calculate the entire elements, all the elements of the tree. So it will calculate based on the values, of course, but in the worst case it will calculate all those. Otherwise, the algorithm is, I think it's the log n is the is the complexity, in my opinion. It will go to the number of levels, and at any point of time you may not cover all the elements. Maybe in the worst case it is order of n, otherwise it is log n, I think. What do you say?
Oh, Suresh, we are going through each and every element, right? Ah,
We
yeah.
don't,
If the
right? Let's say
subtree is not okay.
I just explained, if any point of time either left or right, if the left returns -1, you don't calculate the right, right? So if you look at this algorithm, at any point of time, if the left subtree height returns -1, you don't calculate the right subtree height. You don't need to, right?
But for the
Yeah.
worst case, we have to go through all the elements. So it will
Yeah,
be
yeah.
like,
Worst case is order of n for sure, because you need to touch every element. Yes.
so like in case of time complexity, we take the worst case.
Yeah, yeah. I think it is order of n only. Yeah, yeah. I did not note down the complexity from the book, but that is what it is. Just give me a minute. I can check it. Actually, I have that book. Just give me a minute. So they talked about the complexity. So check balance, right? It is at page 244. Yep, 244. No, they did not talk about. The minimal tree? No, no, this is not the one. Implement check to see binary tree is balanced for the purpose of question balance definition. Okay, page number 244. I'm at 244 only. 240. Yeah, 244 here. Uh, so the code runs order of n time and order of h space, where h is the height of the tree. Yeah, you're right. So this is order of n. Yeah, it's order of n time and order of h space. Order of h in means like the height. So sometime like the space wise, we may take the number of height, order of h. Okay, but it is good. Cool. Are we good? Shall we go to the next algorithm? Okay.
Uh,
Yes.
yes.
It
So
is
like,
minimal binary tree. What is that? Go ahead, Madhu.
yeah, I was saying like for these recursive problems, so we
Yeah.
can dry run on the paper like by drawing a table, like we can make
Because
columns,
yeah.
and
So
it
you
will be
mean like
easy.
number of iterations,
Yeah,
right?
like for understanding purpose. Yeah.
That's good. Yeah, we should do that actually. So let's say this is a node and this is right subtree height and left subtree height, and then we'll calculate the total height. So if you start at A, so we will get the right subtree, right? So then if you start at B, it will go to the D again. So now D, you will get left subtree height 0, right subtree height 0, and the total height becomes 1. Yeah, this is a good idea actually. Having a tables will give more idea. So once we got the 1, here left subtree height is 1, and the right subtree height becomes E. We need to calculate E. So E comes here, left subtree 0, and we want to calculate the right subtree, and then that becomes F here. F left subtree height 0, right subtree height 0, and the total height becomes 1 for that. And we got 1 here, and we got 1 here, and then E height is 2, and we got 2 here. So maximum is 2 plus 1, 3. So this is how you're saying, right? Having values.
Yes. Yes.
Yeah, this makes really sense. Yeah. So now the A left subtree height is 3, and we want to calculate the left subtree C. We got the left and we got the right. So we need to calculate for the C. So C left subtree 0, right subtree 0, and C height is 1. Finally, we got 1 here, and the maximum is 2, greater than 2, and this returns -1. So finally this value returns -1 because the difference is greater than 1. Yeah, yeah, this is a good idea. So we can calculate this kind of we can put the table to understand better. Yeah, I forgot actually, this is the technique we used to follow in the past. Yeah.
Yes.
Okay, good. So we can go to the next algorithm. This is also binary tree. So this is interesting topic. So given a sorted increasing order array with the unique integer elements, write an algorithm to create binary search tree with a minimal height, that is called minimal binary tree. So what is meant by that is they will give you a sorted array. Okay, then we need to construct a binary tree with a minimal height. Okay, so minimal binary tree has about the same number of nodes on the left of each node as on the right. Basically it is almost same. It's not exactly same because it's tough based on the elements, right? If the elements is even or odd based on the number of elements, either maybe one level or two levels is okay. I think only one level is okay, but minimal tree. But the idea here is don't construct something like this. So this is also a tree. This is also like, let's say I'm going to give you a binary tree like this, the array like this, sorted array: 2, 5, 7, 8, 10, 12, 15. Okay, look at that. That's what they said, right? So increasing order array with unique integer elements. So if it is in an increasing order as you are going, it is in an increasing order, and it's sorted. So you can also do like this, like 15, 12, 10. You can start from the end, 8, 7, 5, 2. This is also binary tree, binary search tree. Why not? This is BST, right? What is the condition for BST? The left value should be less than the root. It satisfies that. But is it a minimal tree? It's not minimal. You are having so many, like you are having like the height was is equal to number of elements here. The height of the tree is number of, you are not using the right side, the right side pointers. Basically, it's not minimal tree. Got it? So basically, we
Yes.
need to assign some of the elements right and some of the elements left, so that it is a kind of a nice tree like this. You should start here, and some of the elements here. Maybe one or two elements either here or here. It's fine. This is still fine because you have almost balanced kind of thing. So what they are saying is, try to construct a balanced binary tree, which we just discussed before. Try to construct that. We discussed about, we did not discuss, we discussed about balanced tree, but it's not binary tree. Last time we discussed about ABCD, right? This is just a, we are, it's not a, it's not a binary search tree. There is no numbers, no formulas. Only formula is just we need to balance. We are checking whether the tree is balanced or not. But now basically, using these numbers, we need to construct a balanced binary tree. So how can we do that? So any ideas? So let's say this is the given example. So if I want to construct, what is the best way to construct a balanced binary tree? So how many elements we have? 1 2 1 2 3 4 5 6 7. So 7 means something like, let's assume something like this. Balanced binary tree means only two, right? So 1 2 3 4 5 6 7. Yeah, it's 7 actually. Yeah. So we got the tree. Now tell me what numbers you want me to put in where. What do you want to put at the root in order to satisfy BST condition, and we need to have a balanced values. Any guess? What is the BST rule says? The value of the left node should be less than the value of the root. So value, what are you putting? Some value here,
So
right?
like
Should
if
be
we
less
put,
than the value of the root. Similarly, the value of the right is greater than the value of the root. Yeah, go ahead.
so like if we put 15 in the root,
15 in the root. Okay, let's go with it. Okay, I'm going to put 15 there. Yeah, 15. Okay. Now,
uh,
what do you want to put on left or right?
so 12 on the left
12 on the left. Yes,
and
which
10
is
on
good.
the right.
10 on the right, which is also good. Yes.
But the maximum value is 15. We won't be filling any of the right subtree of 15, right?
Exactly. You're not filling anything. You cannot put 16 or 18 there. There is no 16, there is no 18. So,
Yeah.
exactly. So,
So, is there any way that we can find, since it is sorted, we can find the mid value of in an array, so
exactly.
making
That
the
is
mid
that is
value as
beautiful.
the root?
Exactly. That is exact answer, because it is,
Oh,
they already given this is sorted and it is array. You know, array has very beautiful functionality. Beautiful thing is you can calculate the mid. You can easily find the mid value because you know the length divided by 2. Simple, right? So, and it is sorted. They clearly said it is sorted, and it is in unique elements. They said unique elements, unique integers. See that there is no duplicates. It's a unique integer elements and sorted, and also it is array. So there are three advantages. There are three main important things they gave. So that's a good point. Go ahead. So you can calculate mid value. What you do with it? Go ahead, Karunya.
Yeah, we can fix the mid value as root,
Okay.
such as 8
Yeah,
as a
you
root.
put the 8 there. Yeah.
Yeah. And let us fill 10, 12, 15. We divide it into two sections, since
Mm-hmm.
it has to satisfy the BST
Okay.
condition.
Okay.
So
You divided. You took the root and you put it there. So
yeah,
what are you going to put
and
now?
recursively, let us fill the left side of the subtree first. For
Mm-hmm.
that, again the sorted array, it is, so we'll find the mid value in the left array, which is 5, and make it as a root.
Awesome.
And the left and right, again 2 and 7, we'll fill it out as the left and right.
Awesome. Okay. And similarly, what we do on the right side, same thing.
Same thing.
Calculate the mid value and put it here and do the same thing. Left side, recursive it, put here. There is no more, just one element and put 15 here. This is the exact answer. So now see that it satisfies the binary condition, binary search tree condition, and it is also in a sorted, and it is also in a balanced binary tree. It's a balanced, a minimal tree. This is just a minimal tree of height 3. So I don't think you can create anything less than this. You cannot create a smaller tree than this. You cannot create a tree with height 2. It's impossible because it's a binary search tree. At this level, only two elements are allowed. This at this level, only one element is allowed, right? So this is the minimum. This is the minimal thing what we can build.
Yes, and like it's also recursive in nature, the solution.
Exactly. This is a recursive solution. So just find the mid, put it at the root, and again find the other mid and put it at the root. Those kind of thing. Yeah. Hey Aravind.
To Suresh.
Yeah, man. We just started discussing a new algorithm, so you
Hmm.
just came at the right time. So
Okay, okay.
let me repeat because he joined, right? So we just discussed about the thing. So we last time we discussed last week we discussed about the balanced binary tree, creating a balanced giving a tree whether it is balanced or not. So you can look at the recording of this video or maybe the recording of previous video to previous week to to see the algorithm. So now we discussing about the minimal binary tree. Okay, the
Yeah.
algorithm is basically given a sorted array, sorted increasing order of elements, unique elements. Basically, you got an array. Array has unique integer elements, and those elements are sorted in increasing orderly sorted. Okay. Now write an algorithm to create binary search tree (BST) with a minimal height. So binary search tree with a minimal height, which is like kind of balanced binary search tree. So binary search tree has, so what is minimal binary search tree? Minimal binary search tree is about the say like has about the same number of nodes on left of each node on the right side. So if you look at this one, this is a balanced binary search tree. Okay, so what we got here is this is the array. This is the given array with all the elements. We got seven, like not seven, yeah, seven elements we got. So it is increasingly ordered, right? 2, 5, 7, 8 and all those things. So how can we build a nice balanced binary search tree? Okay, that was the discussion we are doing. So basically you can start anywhere. You can start from root 2. If you start from 2, what will happen? So in the worst case, like let's talk about the drawbacks. If you start with 2, if you start with 2, you need to put 5. You cannot put 5 on the left side. You have to put 5 on the right side, and then go to the 7. 7 has to put here. You know the Aravind, you know the rule of the binary search tree, right?
Yeah, yeah, yeah.
So the value of the left subtree, or the value of the left node less than value of the root, and value of the right is greater than value of the root. So now if as you are going this direction, you get like this. You get a tree like this. It's like you're just building left, right, 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 right. So you are increasing the number of, the height of the tree. It is almost equal to it will definitely equal to number of elements. So the height, finally the height of this tree is 7, which is not balanced, right? It's not minimal, right? So even if
Yeah.
you start with 15, the same thing will happen. If you start with 15, what will happen? You start with 15 there, and then 12. You have to put 12 on the left side. You have to put 10 on the left side. So you are keep on increasing the left nodes, but you are not filling the right nodes. You cannot, because that's all the nodes on the array left side to the 15 are less than 15. So that is increasingly ordered array, right? So the best approach we just discussed about is, what is the best approach? By looking at the diagram, you can see that.
The middle element, we will take it as a root.
Exactly. That is the minimum. That is the best approach. So take the mid element and set it as a root, and then again, recursively execute the same algorithm. Take the left side of the elements, and find the root, find the mid element again, and put as a root for the left subtree. And again, same thing. 2 and 7 here. Same thing on the right side. So take the rest of the elements on the array, and find the mid, and create a root for the left subtree, and then do the same thing. It's a recursively, you do the same thing for left and right. Okay, any questions on this? So now, any questions on this so far? Is it a good algorithm, or do you think any
Yeah.
problems? So there is
What
one
if we don't find a mid in this
exactly.
array?
Exactly. That is what I'm about to tell you. So this is 7 elements. You clearly found the mid value. What happens if it is 8 elements? Let's discuss that. Let's have the same example. Let's have the example like 2, 5, 7, 8. So what I'm going to do is I'm going to close this. So 2, 5, 7, 8, 12, 15, and 17. 1, 2, 3, 4, 5, 6, 7, and let's say 20. You have these men. So how many elements we have? 8 elements, right? 1, 2, 3, 4, 5, 6, 7, 8. So now 8 elements. What we need to do is we need to calculate the mid element. So what is the mid element? If you calculate, if you take 4 elements here on the left side, if you take 4 elements on the right side, there is no mid here. Then what are you going to put it on the root?
12.
Yes, either you can put 12 or you can put 8, doesn't matter. Because if you look at the definition of binary minimal tree, what they said, so it's not like exactly the half and half. So minimal binary search tree has about the same number of elements. About the same number of elements means it's okay to have little bit less elements on the left side than the right side. Right side maybe more, little bit more, maybe one level or two level more. It's okay. So even the balanced binary search tree is also same thing, right? We discussed about last week. So balancing means even though it just one level is greater than one, then it's okay. Greater than one is problem, but the levels are differ by one level, it's okay, right? So we discussed about last week. So let's say this is balanced. Okay, let's say you just added one more. This is also balanced. So the whole tree is still balanced because you just added one level. It's not a problem of adding one level. It's almost balanced, right? So even if you add something element like this, then it is not balanced because you are adding more and more to the right side. This whole subtree has level 1, 2, 3, 4 levels. This one has only just 2 levels. So if the greater than the levels like 4 minus 2 equal to 2. So the difference between these two, left subtree and right subtree, is true. That's where it is imbalanced. So if you don't have this one, if you don't have this node, the height is 3. 3 minus 2 is 1, which is okay. Yes, is only one level difference between these two. Similarly, if you are constructing this minimal binary tree, there is no hard and fast requirement that it must be equal number of elements on the right side or the left side. So there is no requirement like that. So you can start with any of those nodes. So why do you take 12? So let's say how many elements we have? 8. So what is the way to calculate the, actually we forgot to do that for the other algorithm. So we can do the same thing. So in the previous algorithm, we had 7 elements, right? So how do you calculate the mid value? How do you calculate the mid element? 7 by
2.
2. So if you do 7 by 2, what will happen? 3.5 or something. But we don't take 5. We don't take point values, because if you take just integer value, what will happen? 3, right? So that means this, if you look at the index 0, 1, 2, 3, and this is 4, 5, 6, 7. Sorry, this is 7. So now in the previous algorithm, we had until here only 7 elements, 0 to 6 we have, and we take the third element, which is number 8. We take the 8 and we put it 8 as a root. But here, what is the size here? Size is 8. Total number of elements is 8. 8 by 2 becomes
4.
4. Now, fourth element is the mid. So that's why we take the 12. This is the index 4, right? So if you take the 12 here, what will happen on the left side? So we'll calculate the same thing for this one. We'll calculate the same thing for this one. So now we are taking 0 to 3, and again the same problem here. How to calculate the mid element here? How many number of elements here? We have 4 elements, right? 4 by 2 equal to 2. So take the element at the location 2. That means 7, right? You guys following so far?
Yes.
Yes.
So now you got the 7, you put the 7 as a root. Now we got again recursively go back. We have two more sub arrays. This is one sub array with 2 elements. This is another sub array with 2 elements. So here I'll again the same. We have 2 elements, 2 by 2 equal to 1, and take the 1, that means like 5. Take the 5 as left here and put it here. Now if you recursively took it, there is no elements on the right side. There is only one element on the left side. So 2 goes here. Okay, there is no elements per 5 on the right side. Now let's go back to 7. 7, there are some elements on the right side. So only one element, put 8 there. So there is no need to do any recursive there. Done. 2, 5, 7, 8, 12 is also done. Now let's recursively do the same thing for this one. How many elements here? We have 3 elements. 3 by 2 equal to how much it will be? Integer value.
1.
1.
1. But if 1 means, are you going to take the value at 1, which is 5? Are you going to take the 5 and put 5 here? No, because 5 already placed here. So this value tells the offset. Basically, hey, you are calculating on this particular subarray. Okay, take the first value, or take the index 1 from the beginning. So if you are taking this one as 0 and 1 and 2, take the value at 1 here. That means you need to take the 17 here. So if you just divide this like this and don't just blindly take the value with this index, what we need to do is we need to take the mid value, and we need to add the mid index, this one, to the beginning. This is the starting. What is the starting index here? 5. 5 plus what is the mid index? 1. So 6. That is the value you need to take, which is 17. Did you guys follow there? So basically, when you calculate this one, you need to add this integer, add this mid index to the starting point. The starting point is 0. That's why you take 0. So 0 plus 2 is 2, 0 plus 1 is 1, but that's okay. But here, when you're calculating this one, you need to take the starting index plus this index. So starting index is 5. 5 plus 1 is 6. So that's why you are taking the element at number 6, which is 17. Okay. Now you recursively calculate the same thing. take the left sub array here and take the right sub array here and recursively do it. So luckily we have only one element. If there is only one element, you no need to do any divided by 2 or anything. Simply put 15 there as a left and 20 there as a right. See this. Now we are done. This is a minimal binary tree because see it's a minimal. On the left side, on the right side you have 2 levels. On the left side you have just one more level, 3 levels. That's okay because where can you put 2? You cannot put 2 anywhere, right? Because it's a binary search tree. So this is minimal binary search tree. Is it clear to everybody, or any questions or any concerns?
Yeah, it's clear, Suresh.
Yeah, it's a very interesting algorithm because how to convert a sorted array to a binary search tree. So I'm going to show the algorithm if you guys are already clear on this approach. Okay. This is balanced binary search tree. This is balanced algorithm and minimal. Here is the minimal. Yeah, minimal binary search tree. Ideally, I should stop here and ask you to write the code. Shall we start that in that format? People will just leave.
No, 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 no. We'll try
They say,
some.
Suresh, I have some work. Bye. But that's important actually, writing those algorithms, that's really important. What we do here is we used it to do 3 years ago when I go to the libraries where we met like all these SD folks. We meet and we just discuss like this in the board on the whiteboard. We discuss about we will discuss around 10-15 minutes or half an hour. We'll discuss about different approaches, and somebody will go to the board and explain, hey, finally we'll figure out, okay, this is right algorithm. Okay, now write the code. Then everybody will silent for next 15-20 minutes, and the people will write the code. And there are few folks from Amazon and Microsoft. Those are the people who conducts all these algorithms. They will come to us and they will validate and see the code and say, hey, there is a bug, and find out. They don't say where the bug is. There is a bug, is it correct or not? Simple. He is IIT candidate, that guy who created that company, that non-profit company, SD algorithms, SD, the skills, right? This SD skills person. So he's really nice. So that guy used to come to us and simply say, hey, there is a bug here, find out. So that's how it is actually. When we are practicing, that really matters. So Vivek, yeah, this is the guy. So he is the one who just started like a couple of years ago. This is the guy who started this whole, SD skills. So I don't know, maybe we are not meeting these days in libraries, but he used to do that. So once you find the algorithm, you need to write. So maybe we'll practice that as well. So that will make more because that will make you to think and write at the same time, right? Rather
Yeah,
than
it's helpful.
otherwise, I will just explain here. You just listen, and then maybe you may not remember unless you practice again. You need to put pen and paper, and you may need to watch the video again, and you need to practice again. So, but if you practice in the same session, that will be more effective. But I know we are in a remote situation, and the other thing is it's already night there, so I don't want to wait for another half an hour to write the code. So anyway, so that's very simple. Here is the algorithm. I'm going to explain and show the algorithms. You guys know already. This is the node data. Here is integer data, left and right, and here is pretty basic node class here. And here is the thing. Okay, hello world. This is creating minimal binary search tree. Binary search BST actually. This is binary search. It's not binary tree. Binary search tree. So now let's say this is an odd number of elements. Here I took 9 elements, and here is the even number of elements. I took 10 elements here, and I took 0 elements. These are 3 different use cases. Let me know if you find any other use case. This is very important in interviews. When you write the code, they will ask you, hey, if you're only taking one element, say it's everything is done, I took 7 elements or 9 elements is done, then interviewer will ask you, is this the only use case? What are the different use cases? What are the different inputs, right? So this is another input. There could be an even number of elements is another input. There could be 0 elements. This could be another input. When you're writing an algorithm, when you're writing a method, you need to think about all these possibilities. Input can be as dirty as possible. You never think that this is beautiful, always 9 elements. Never think that always 7 elements or always odd number of elements. There is no requirement given like that. Only requirement they gave is these are unique elements, and these are increasingly sorted, and these are integers. That they already given that. So you don't need to worry about whether these are sorted or not. You don't need to worry about whether there is a duplicate or not. We don't need to worry about any of those concepts because those are already given. Only thing is they did not say whether the array has even elements or odd number of elements. They did not say whether is there any possibility of zero, you know, 0 number of elements. Array may contain 0 elements, right? These are the 3 different use cases. So I tried with this array, array 2, array 3. So so we need to make sure our algorithm should not break for any kind of input, any of these 3 use cases. Okay. So now create minimal BST, and I'm printing in order sort. So print in the sort order. Basically, print in sort order is basically I'm printing in order traversal. Once you create the tree, I'm sending to the in order traversal. Then you see the elements in the sorting order, but they already given in sorting order. You will see the same output if you print in the in order fashion. So that's why I printed in pre-order fashion. Pre-order means, what is pre-order?
Root will be the first thing,
Mm-hmm.
and
And
left,
root,
right. Root, left, right.
exactly. It will print the root, it will print the left, and then it will print the right. So that way we need to make sure whether we got the 12 initially or not. So 12 has to print first. So for this particular input, 12, and then 7, and then 5, 2, 8, 17, 15, 20. That is the pre in order, basically in order, pre-order, print in pre-order. So I shouldn't say print in pre-order, it will be confusing. So I would say simply, let me rename. So there is a rename, right? Is it shift F6, shift F6 probably? No. Okay, that's okay. So yeah, rename symbol. So print pre-order. That way it will be easy, because in means in order, we don't take that. So pre-order, basically we are printing in a pre-order fashion, which is root, left, right. But anyway, let's talk about the actual algorithm. Printing is the last step. But what is the actual algorithm? What are we doing here? We are simply calling this minimal binary search tree, and we are calling this algorithm, and simply we are going to this one. So create minimal binary search tree. So we got the array, sorted array. So what are we doing here is we are calling one more method called minimal binary, like create minimal binary search tree. Same thing, create minimal BST with a different number of arguments. We are sending start and we are sending end. So basically, when you initially start, what is the starting value? 0, right? And what is the length? Like the last value is sorted array dot length minus 1. That is the ending index. Basically, we are sending starting index and ending index. Okay. So we call the create minimal binary search tree, and at any point of time, if start is greater than end, okay, if start becomes greater than end, return null value. So this method also returns node. Even this also returns a node, which is our tree node. Okay, at any point of time, start greater than end, return null. Otherwise, calculate the mid. How to calculate the mid? Start plus end by 2. That is the mid value. Okay, so now sorted array of mid. So they are saying start plus end by 2. Oh, the way I explained is different, and the way we calculated is different. So now let's take the example here. Let's take the example here. So 15, 17, 20. If you take this subarray, what is the start index?
5,
5. And what is the end index?
7.
7. So 5 plus 7 by 2. What will happen? 12 by 2. This will give you the exact middle index, which is 6, which is 17 here. The index is 6, right? This is another way of doing it. You don't think this is 3 values and 3 by 2 equal to 1 and then add 1 to the starting. That is also 6. This is another way. But rather than counting the elements and doing it, we can do this way as well. Similarly, if you want to calculate for this whole array, 0 plus 3, which is equal to 4, 4 by 2 equal to 2. So here 7 is the mid. That's why we got 7 here. Right? This is just another way of doing it. This is how they're calculating mid index. So start plus end by 2. We got the mid index. Here is the mid value. Sorted array is there. And take the mid element and create a node. So whenever that's what we just did, right? Initially we got the mid element 12. We created a node and we put the 12 there. And now you need to do the left of it and you need to do the right of it. So how are you doing left? Node dot
Recursively.
recursively root dot left equal to, again create minimal binary tree, sorted. Now what we need to do, start mid minus 1. We already know mid value. Here is the mid minus 1. This is the subarray for the left side recursion, and mid plus 1 to length, mid plus 1 to end, that is the subarray. Even though we are sending the whole array all the times, don't consider the thing, just consider from this to this. This is the start and this is the end. For the left side, start is start but end is mid minus 1. So we are always setting the boundaries. When you start initially 0 and length minus 1, take the whole elements, find the mid value, create the root, everything. But when you are doing for the left side, after you create the root, when you are doing for the left side, take the array, but start from start, take until mid minus 1. So here is the mid value. When mid value is 12, 4, like it's only 3, 0 to 3 is for the left. And then 4 to 7, mid plus 1 is 4, right? So here what we do is for the right side, mid plus 1. Mid value is 4 here. 4 plus 1 is 5 to 7 for the right side recursion. Okay, this is how it works. Again for the left side, again it will do the same thing. It will take the mid value, put the mid value, and again it will call for left side and it will call for right side. So when you're calling right side, so that's where it happens like plus and minus. So when you call for 8, what we need to do is 2 plus 1, right? So start at 3 and end at 3. So then is start is greater than end? No. Then it will do the mid value. It will create it. Now start becomes like 3 and mid becomes like start becomes 3 and the end becomes 2 because mid minus 1. Start is 3, end is 3. But now we are minusing. We are doing minus value, which is like 2. So mid value becomes 3 plus 3 by 2 is 3, right? So when you say, when you are calculating at the 8, only for the 8, let's take the 8. Okay, the subarray is 8 and start value is 3, end value is 3. That means mid value is 3 plus 3 by 2, which is equal to 3. So you take the 3 and you put the 8 here. Now what happens here is you need to calculate left for the root, right for the 8, left for the 8, right for the 8. So when you are doing this, we call this one and start equal to 3 and mid becomes 2, because 3 minus 1, 2. So what happens? That is situation where start is greater than end. Start is greater than end, it will returns null. That null becomes the left for 8, and also same thing for right. Null becomes left for 8, right for 8. That's how you are setting the null for left and right for 8. That's where it stops the recursion. So put a breakpoint and see how this works. Are you guys following so far?
Yes, yes.
Yeah. So this ending condition is very important when you are writing recursion. When are you going to end the recursion? That is very, very important. So this is where we are ending the recursion. When you go to the all the way to the left of the tree, or when you don't have any elements, right? If you are taking the array with 8, that's it. You calculate the 8. There is no elements in that subarray, only one element. That is the situation where it becomes start greater than end. Then you get the null value, and null value will be assigned to left of the particular element, and null value will be assigned to the right of that element, and that finally that element will be returned. This finally 8 will be returned, and that will become the right of 7. It will go all the way to the top. Okay, so let's run this program and see. Are you guys following so far, Aravind and Modit? Let me know if any questions. Aravind, is it clear?
Yeah, Suresh.
Cool. Yeah. Okay, so now we are calculating for the first array. Okay, let's continue and see this. Is the root value? Okay, I don't want to go through the entire thing. Okay, now look at this. Oh, okay, okay, this is the value. So 257, these are the initial values, and here is uh, this is the pre-order. Okay, this is the input given array, and this is the pre-order of the elements. Okay, so now let's build a tree for these elements. Just give me a minute. If I build a tree, then we can easily understand. Okay, so
Why is there a need of pre-order traversal? Mm. I mean, are we using
nothing,
it to?
just for printing purpose. See,
Okay.
you can print in any order. So how do you print the tree? You cannot represent the tree like the way we are drawing, right? It in order
Okay.
to print like this, in the console, it's not possible. And if you want to print like this, you need to write the graphical UI, something different algorithms. You cannot print like this, right? So the printing a tree, either you need to do either in order or pre-order or post-order, representing in 3 different traversals, right? Or of course we have level order, we have depth first traversal. There are different traversals, but very primary thing is either pre-order or in orders, right? So the reason why I took the pre-order is, I will tell you. So this is what we have, the tree, how the tree will be constructed here. 8, right? So if you take these elements, so this is the elements. Okay, 8 will be the root, and then what is the root for the rest of the elements? 6, probably 6, right? 6 will be here, and then 5 will be here, and maybe 2 is here. Is that the way? Yeah, 8, 5. Oh no, I think it took the other way. I think it took like this, probably 8, 5, okay, and 6, 2. This is how it created the tree. And I think after that 10, yeah, 10, and then 9, and then 15, and then 20. Okay, so now if you look at the pre-order is always like this, right? The tree, and then left, and then root, left and right. So now 8, 5, after 5 you need to calculate 2, and then 6, and then oh, you got the 7. I forgot the 7 here. Shit. I think this is how it created. So if I reduce a little bit here, so 7 created here. Yeah, 7 created here. Yeah, and then after 8, 10 created here. Yes, this is 10, and then 9 created here, 9, and then 15, 20. This is the thing they created. This is how the tree created, right? So if you look at the pre-order, 8, 5, 2, and 6, 7, and then 10, 9, 15, 20, right? This is the pre-order for the tree. Are you guys following so far?
Yes.
Yeah.
Yeah.
So yeah, so this is same for the other tree. So this is for the second one, which is having 9 elements. 9, yeah, first one have 8 elements, and this one have, no, first one have 9 elements, second one have 10 elements. So for the 10 elements, it's the same thing. It will do the same thing. It just added 25 at the end. So, and 0 elements, for the 0 elements you'll get nothing, right? So but algorithm should not break. That is very important. So if I put here and see what happens for the our array 3, we got null. So because array 3 is 0 elements and it goes here, so array 3 is 0 elements and 0, and length is also 0 minus 1. So length becomes like start becomes 0 and becomes minus 1. So start is greater than end, return null. So null will be returned as a root for the third array. Okay. So if it is null, you are not printing anything. If you go to the print in order or print pre-order, anything, if the value is null, we just return the algorithm. So either pre-order or even in the in order traversal, we do the same thing. So you don't print anything for the third third element, the third array. Okay. Yeah, that is basically the full algorithm. So look at that. It just it's hardly 6 lines, right? So 1, 2, 3, 4, 5, 6, 7 lines. Just hardly 7 lines of algorithm, but it took more than half an hour to explain and half an hour to understand. See how difficult it is. That's the magic of the algorithms, right? Is it clear, or any questions so far?
Clear, Suresh.
Clear to me.
So this is very important, algorithm, I would say, because how to construct this is the way, this is algorithm where it will tell you how close the sorted array and the binary search tree is. So sorted array is nothing but a binary search tree with all the indexes. So you can manage a whole tree using an array. You no need to create array. There is one more algorithm I'm trying to find, where it will give you left nodes, right nodes, everything out of an array, out of the sorted array. Without creating a separate root node, without creating a separate data structure like this, you can manage entire tree using array, because it's all indexes, right? You can easily calculate what is left, what is right, just by looking at this. If the 8 is root, you can calculate the left of it, and you can also calculate the right of it. Based on the indexes, it will calculate. So that's how we did it. So we created a tree out of a sorted array. Okay, cool. I hope it really helped, and I will send you the link for this code. This is part of the code cracking the coding interview book. So I will send the link of this code and also send the recording of this video. So please, revise and also share with your friends. So invite your friends. That is what I'm telling. Like I'm putting my efforts to explain. If we have more people, it will be more helpful. So I hope maybe any of your friends are trying, or maybe if they want to try in the future, they can just listen also, right? They can just pay attention for 1 hour. They can listen something, and then when they are preparing after 2 years or 3 years, they can easily recollect. oh, I know this problem, I listened, and we have a recording as well. So it's very, it makes them to easy, for when they are trying for interviews in the future. Okay, so please share this and invite the people to join. So if more people are there, more they will get more benefit. So next week we will discuss the heap algorithms. There is lot of questions on heap, very important. I think I missed one more thing, the first common ancestor. That is also very important. I will try to cover this one, the first common ancestor, and then heap. And there are different trees like AVL trees and other trees, B trees. There are different number of trees. I don't know whether entries go that far. So I will see if I find the algorithm for AVL tree. I will see. Otherwise, we will jump into the graphs. Graphs also so many algorithms. So there are a lot of algorithms in graphs. In companies like Amazon, and those people will ask you, hey, how you calculate the distance, how the Uber is working, how the Google Maps is working, how the flights. If you take the Bombay and Hyderabad, how you calculate the flights between those two cities, what is the shortest distance, all those things are graph algorithms. Very, very important, very, very deep, and very little bit complex wise. It is still complex algorithms, but I did a couple of graph algorithms. Look at here, 1, 2, 3, 4, 5, 6, 7, 8, 9, around 9 algorithms I practiced 3-4 years ago. I can explain those different algorithms, shortest path algorithms, and directed graphs, connected graphs, different types of graphs in algorithms. I will write down those and I will explain one by one. So it's very important. Please connect with your friends and invite them. And there is another last concept is sorting algorithms. I practice around 10 types of sorts. I have really nice PDF. Um, it's very fascinating. That PDF realized me, oh, these many sort algorithms, bubble sort, quick sort, insertion sort, merge sort, and selection sort. It's so many, like so many different sorting algorithms. Very, very interesting. And I'm going to explain those in the upcoming weeks. Okay, cool. Yeah, let me know any questions. Sounds good.
It's
Yes,
clear,
Yeah.
Suresh.
yeah.
Just we have to practice once. Nothing else.
Exactly. Yeah. I will send the links and everything. Cool. Awesome. So let me stop recording here. Okay. Have a nice evening and have a nice week ahead.